Hello everyone, I am Gaurav Somani, and today we will start with the remaining portions or topics from the basics of statistics curriculum that we could not cover into the last video. So we'll start with the thought of quintiles, quartiles, deciles and percentiles. Basically it is more to do with arranging the data into a sequence and like from ascending to descending, and the technique is more used in terms of determining and assigning basically a kind of a probability or data segregation points below a particular point into your data range. So how we go about it is, when we talk about quartiles, we break the entire data into 4 quarters. The first quartile point will suggest that at below this particular observation 25% of data is lying, and second quartile says below a particular observation 50% of data will be lying across. Similarly, we can break the data into 20s also, that is 5 halves, and in that case the first quintile will suggest below a particular point 20% data is lying. Maybe if it is the third quintile, so it is below that particular point 60% data is coming across, and that can again be used as a probability measure in terms of anticipating future, that beyond a point what all possible values of data can come below a point and above a particular point in your data range. You can break them into deciles, that is 1 by 10s, 10 halves, or maybe the smallest fraction could be percentiles. So in any case, whichever ways you break it, to get to know the position below a particular point where the data is lying, we can simply use this formula, which is n plus 1 multiplied by y by 100 for whether it is a quartile point that you want to get, or maybe a decile or a quintile or even a percentile point. Let's move ahead and look upon to one of the most important part when it comes to data distribution, and we're referring to the normal distribution. The key of normal distribution in statistical decision making is very important, as in if the distribution is normal, we can go to hypothesis testing and test our statistical findings with their significance. So let's look upon to the key properties of a normally distributed data. Among all, there are 5 parameters that we talk about. A normally distributed data is purely described by 2 parameters, that is mean, which is denoted by the sign mu, and variance, which is basically denoted by the sign sigma square. We say the skewness is 0, which means that mean, median, mode in the data is same. So it is entirely symmetrical. As you move left or right to the midpoint, you have data distribution which is very symmetrical. Any random combination of normally distributed data is again, as they say, normally distributed. So a linear combination of normally distributed random variables is again normally distributed. That is another property with the normal distribution. The kurtosis, we say, is 3, which basically represent the height of the bell, and that is measured by kurtosis. We'll talk about skewness and kurtosis in coming slides also, but the kurtosis value got to be 3. So the bell height, which is measured by kurtosis, got to be 3 for a distribution to be normal distribution. And one of the key property of normal distribution is, as you move far away from the mean, the possibility of outcomes reduces, but it never goes to 0. So the probability of any outcome is there. From negative infinity to positive infinity, all possible values can occur as far as the normal distribution is concerned. But as you move far away from the mean, the probability of outcome keeps on reducing. If the data is normally distributed, we can basically use it at the same time to create confidence intervals in terms of where possibly the expected value would be lying, and what is the probability associated with an expected value to lie in a particular range. We talked about into the basics of stats video 1 about how do we read risk. So if the expected return is, let's say, 10%, okay, so pen is 10% with a risk of 15%, we create a kind of a range with this distribution, which is, let's say, -5% to 25%. Now the thing is, what is the probability that your actual outcome will fall in this range of -5 to 15%? In that case, if the distribution is normal, we say almost 68.26% probability is there that the data will fall in that particular range. So if you move from your mean left and right 1 standard deviation away, the probability of the data or number of data points which have come in past if the new distribution is normal is around 68%, and this is how we would be assigning maybe the future possibility of outcome to be in the same range. And maybe if at 68% chance you feel it's very less enough, because there is still 32% probability that the expected value may fall out away or out of this particular range, what you tend to do is you want to be more confident. And how do you increase your confidence is when you increase the parenthesis. So you increase your confidence by increasing the bandwidth. And if it is a normally distributed data and we say you want to be 90% confident, you got to move almost 1.65 times the standard deviation away from the mean. So x bar plus minus 1.65 standard deviation if you're going to be 90% confident. If you're going to be 95% confidence in the normal distributed data, we say you got to move 1.96 standard deviation plus or minus. And if you got to be 99% confident, then you say you have to move around 2.58 standard deviation away from the mean. In all the cases, see, as you far away move from the mean, your data points start coming more within the bandwidth, and the confidence of having a possible outcome into a particular range increases. The other approach of determining how much would be the probability of an outcome into a particular range could be the Chibisway inequality. Now Chibisway talks about irrespective of the distribution. So he is not saying your distribution got to be a normal distribution. Whether it is a normal distribution or not, he talks about one thing, that the number of possible outcomes or probability or confidence by which maybe an expected value will fall into a particular range would be 1 minus 1 upon k square kind of a thing, where k represents the number of times standard deviation you deviating from the mean. So if you are deviating 2 standard deviation away from the mean, it says almost 75% observations will be falling. You deviate 3 standard deviation, 89%, and you deviate around 4, it is 93%. That's how Chibisway talks about irrespective of the distribution, a standard working that he has worked upon. Let's talk about, when we're talking about data distributions, we talked about 2 key properties of normal distribution. One of them was the skewness is 0, and the other one was kurtosis is 3. So let's look upon to what basically skewness means. So skewness means that the mean, median, mode is same. That is, the data is symmetrically distributed. That's what is the basic thought with normal distribution. As you move left and right some standard deviation, or you travel a distance from the mean left and right, if the distance is equal, the number of outcomes which will fall to the left and the right tail will be the same. That's what the basic thought of skewness. And how do you measure skewness is basically, if we talk about, let's say, a set of observations or deviations. Let's say if this are the deviation which is -3, +2, -2, maybe +3. So this is like a symmetrically distributed deviation. When you move left or right to the mean, you have got same data points in terms of deviation. There is an observation 3% down, or there is an observation 3% up also. This is purely a symmetrical distributed data. Now if you go to the third power of it, if you sum across all the deviation at the first power, the sum of all deviation will be 0. If you go to the third power, in terms of the cube of this deviations will have values like this, and the total will be again 0, and that says that the data is symmetrical and the skewness is 0 because mean, median, mode is same. But if let's say rather than -3 in this example and -2, these are my observation, the mean deviations are still 0, but when you go to the third power, what you get in terms of data points is -64%, +8, -1, +27, and the summation is a negative value. And that says that the data is negatively skewed. So what is basically a negative skewed data is suggesting is there are some extreme negative values or outliers which are coming away into the negative side. When you say the other half, when it falls, the stock falls more, maybe you'll have negatively skewed data distributions. Similarly, you could have a positively skewed data distribution also with positive outliers. So in a symmetrical distribution, there are no basic outliers, right? So that's how you take care of the skewness. If you look up out of the formula also, as you go to the third power, you basically can calculate the skewness. If the summation of the numerator is 0, we say the skewness is 0. And as far as the other property of normal distribution is concerned, which is kurtosis, which is talking about the height of the bell-shaped curve, says that for a normally distributed data, the kurtosis got to be 3. And if the kurtosis is more than 3, we say the data is elliptokurtic, or the distribution is rather elliptokurtic. It is more elliptic. The height of bell is more than what is supposed to be at 3 levels. And because of that higher height, what is happening is there is more possibility of data close to the mean. At the same time, just because you have just more or less skewed that particular nozzle, so the tails have become fatter, then there is more possibility of data far away from the mean. And if the kurtosis is less than 3, we say it is platykurtic. And if you have compressed it, so the data gets segregated, it gets more distributed, and there is more amount of data far away from the mean compared to a normal distribution. And as far as kurtosis calculation is concerned, we need to go to the fourth power of deviations. So as you go to the fourth power of deviation, that is how you calculate your kurtosis. If your kurtosis is greater than 3, we say the data is elliptokurtic, the height is more elliptic. If it is equal to 3, it is normal distribution, and we say it is mesokurtic. And if it is less than 3, the kurtosis value, then we say it is platykurtic. Compared to a normal distribution, in a platykurtic data, the data is more far away distributed from the mean. In a elliptokurtic data, you have more observation close to the mean. At the same time, you have more observation far away from the mean. So that's all with regard to the basics of statistics. We've covered the remaining portion today. Thank you so much for watching. Best luck for your examinations.